everyone. We're going to continue on with logs and exponents, and the next couple of videos are just going to be working some examples. So we're going to look at 3 examples using log and exponent equations. First one is we have basically looking like an exponent here. We have 100, 7x plus 1, and 1,000, 3x plus 2. And we could try logs, we can do something else, but I see a relationship between the 100 and 1,000, and this is going to be a common type of problem. If we could change this to the same base, say 10 to the second power, and this is nothing more than 10 to the third power, we can use our 1 to 1 if I have something of, like, say, a to the m is equal to a to the n. We know m is equal to n, so we're going to set the two relative exponents apart because that equal sign is very powerful. And that's exactly what we're going to do. We're going to have 10 raised to the second power times 7x plus 1 is equal to 10 to the third power of 3x plus 2. All right? So here we go. We're going to distribute that 2. Well, we could cancel these out and just put 2 times 7x plus 1 is equal to 3 times 3x plus 2. Distribute, so I'm going to have 14x plus 2 is equal to 9x plus 6. So I'm going to subtract 9x on both sides. I'm going to subtract 2 on both sides. And I'm going to get 5x is equal to 4. Therefore, x is equal to 4/5. All right? Not too bad. Let's take a look at another example where it won't be so straightforward. So we got a funny thing going on here. We have 7 raised to the 9x, that's not typed up very well, is equal to 15. Well, one of the things we could do is we could take the log on both sides, as long as the log is the same, base 10, base whatever. As long as the base is the same, we can do the 1-to-1 property again. So I'm going to go ahead and do this as log base 10 of 7 to the 9x is equal to log base 10 of 15. All right? And then I'm going to use the exponent property. I'm going to bring this all the way to the front. So I'm going to have 9x log 10, 7 is equal to log 15. All right? Now the next thing I'm going to do is I'm actually going to divide by log base 10, 7. I'm just going to use the algebra. I'm going to divide this by log 10 and divide this by log 10 to the 7. Okay, log 7. So that leaves me with 9x is equal to log 15 over log 7. Now, when I had to replace my hard drive many months ago, I lost my Casio emulator, and so I don't really have a calculator I could bring up here. I don't want to buy one right yet. So I could put this in the calculator now and get 1.39. I did this on my calculator on my desk. Or better yet, I'm going to multiply by 1/9 or divide by 9, and I'm going to have x is equal to 1/9 times log 15 over log 7. This is a calculator-ready answer. So I could have done this. I could have done 9x is equal to 1.39. That's rounded, of course, divided by 9. And I would get x, this is approximately 0.15. Okay? Or I could put this in the calculator. I'm also going to get x is approximately 0.15. Whenever I get around to getting a new emulator, I could get one for free, but I already did that and my time expired on it for my trial period. All right, so let's go ahead and next one. So here we're going to have a natural log situation. And again, I could apply any log of the same base. So if I'm going to do that, and I'm going to have an E, Euler's number involved, I'm going to go ahead and do ln of e to the negative 0.3x is equal to ln 5. And then we can use our inverse properties. We have basically log base e raised to the e power, and that's just going to cancel that out. So I could just slice right through this, and I'm going to have negative 0.3x, negative 0.3x is equal to ln 5. Divide by negative 0.3, put that in the calculator, and then knock it out. And when I do, oops, let's make sure we have the negative in there. Should put a 0 right there just for fun. And once I put that in the calculator, this is my calculator ready answer. I'm going to get x is equal to about negative 5.36. Alrighty, so I'm going to go ahead and upload these and do a few more examples on the next video.